All right. Turns out that it's possible to multiply a matrix times a vector. And it looks a little weird at first, but it'll just be another way of rewriting a system of equations. Like we've already sort of thought of rewriting a system of equations as a linear combination of vectors. This will just be another way. But let me give, well, let me first say, okay, so we can define matrix times vector. Not all the time, there'll be some conditions on that, but I want to motivate this though with a one-dimensional example. So consider, let me try motivation. So consider something kind of dumb, like the equation 3x equals y. Now, you could think of this, or maybe I'll even just say 3x equals 6. This is one equation in one variable, one linear equation in one variable. And if you think about it, let's see. So if we wanted to put this back in matrix language, we could say, you know, there's lots of dumb things you could say here. You could say the system is, you could rewrite it as an augmented matrix, like 3, 6, like that. You could let A be the coefficient matrix. It's a 1-by-1 matrix. Again, kind of dumb. X could just be the vector X. And maybe, you know, sometimes we call the augmented column B. So maybe B is the vector 6. Well, my B's and my 6's look kind of similar, so maybe that was a bad choice. But we'll go with it. And so this is kind of silly, but you could think of it this way, right? And if we do that and we actually replace everything in this equation with each of these things, then we could rewrite (3x equals 6) as a matrix A vector X equals vector B. And it's kind of like, and you know, up here in this equation up here, there's an understood multiplication sign right there, put a little white dot there for it. And so there's an understood multiplication sign here, and this, so in a really silly way, you can think of this as a matrix times a vector. Right? And it has the same content as the as a system of equations. I mean, it's a system of one equation in one variable, but it's still a system, quote unquote system of equations. So we could generalize this. What if we had something like, let me just make something up, 2x1 plus 3x2 minus x3 equals 7, and negative x1 maybe plus 0x2 plus 3x3 equals negative 4, something like that, right? Well, again, there's a coefficient matrix A. So the rows are 2, 3, minus 1, minus 1, 0, 3. There's the vector of the unknowns, x, and there's the vector of the numbers after the equal sign, 7, negative 4. And what I want to do is I just want to write this again to sort of stand in for this system. And so, and it just turns out mathematicians do that. Like, in some ways, what you do is you write ax equals b again for the system. And in some ways, we can think about this as it's almost like we're factoring the left-hand side. It's almost like we're factoring this into a matrix times a vector. Let's see if I can write that down somehow. So, we're going to take this and we're factoring it. I'll just put in quotes, factor the left-hand side, just the left-hand side. Maybe I should put a circle around that. Factor as matrix times vector. Right, in that we're saying we can rewrite, we have this sort of, this is really a vector, the left-hand side of this. Actually, let me do something. Let me actually put the 0 in here really explicitly. Plus 0x2 plus 3x3. And we're really rewriting that as the matrix 2, 3, minus 1, minus 1, 0, 3, times the vector x1, x2, x3. And we're setting that equal to the vector 7, negative 4. So in some ways, this is a convention, but, it's actually sort of a nice convention, or a motivated convention, that we're sort of rewriting this as this. And yeah, so that's the idea. But there's a couple different ways to think about this. So we define, to be more general, well, first, let me make a consideration. Notice what we have to have for this to work, right? We have the same number of variables as coefficients in a given equation. Same number of variables as coefficients in a linear equation, right? Even if some of the coefficients are 0, we still think of them as being there. Which means we have to have, you can't just multiply any matrix times any vector. You really need the number of columns of the matrix, the coefficient matrix A, has to equal the number of entries, basically the number of variables. The number of, but in terms of a vector, that's the number of entries in X. Right? So the way we'll say this to be super general is if A is an M by N matrix, so something that's gonna be annoying the whole time is that we use M for the number of rows, N for the number of columns, and X is in Rn, then we can define A times X. And it's also worth saying that that we have this, there's a couple different ways to define this, right? We can just give it sort of purely as a formula. If you really want to write like, A11, if I really want to write the matrix with double subscript, sort of the general. So that's, what the general matrix looks like. A M1, A M2 through A M N. Geez, those don't look like M's, do they? Let's try to be a little better with that. M2, M, N. And then times X1, X2, dot, 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 through Xn is just by definition this, this A11 X1 plus A12 X2 dot, dot, plus A1N Xn, and then same thing through the other rows down to wow, that looks like a n, not a 1, 1, 1, 1. A m1 x1 plus a m2 x2 plus dot 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 plus a m n x n. There's a couple things to notice. There's a couple different ways to write this down. So the first thing I would say is if we look at something like the first, it's almost like we're multiplying rows of the matrix times columns of the times the column of the vector column vector to get this entry right here. And that's a number, right? This is a number. This is a vector. This is a vector. But this is a number. And in fact, you've probably seen this way of multiplying two vectors before. If we let's just call this vector R1. So this is a row vector through Rm. This is also a row vector, but then this is the column vector X. Then do you recognize what R1 times X, what I'm really doing to get R1 times X? It's really this thing called the dot product, which you probably remember, right? Where you sort of take two vectors and you line up the entries. Like I multiply the first entry times the first entry, and then I multiply the second entry times the second entry, and then so on to the last entry times the last entry, and then I add up, I take all those products and then I add them all together. So this is really the dot product. So, and remember the dot product of two vectors does give a number. So this is the dot product. R1 dot X. I'm excited, so I'm gonna put an exclamation point, but I'm putting in parentheses so we don't think it's factorial. Okay, so that's the dot product. So it's kind of funny. It's really like, you could say, if you look at it this way, you could say A times X, if that's the matrix whose rows are R1, R2 through Rm. Oh, that's not where that goes. That's a matrix whose rows are like that, times, notice over here, these are all vectors. These are row vectors. These numbers are just going to be numbers, entries. Actually, I don't even want to write this. Sorry, I just want to write X. It's really R1 dot X, R2 dot X. And honestly, if you multiply a matrix times vector by hand, this is sort of the way you end up doing it. You sort of think about the row times the column, and you can sort of practice multiplying. So that's one way. This is sort of the row. This is sort of row dot product multiplication. Sort of what we're doing right here. But you can also think of this as weighting the column vectors is another way to write this. So another way I could write this is to say, let's think about A as having columns, C1, C2 through Cn. Then we've already sort of seen this, right? We can rewrite this expression up here. If I take this down here, I can sort of rewrite it as, let's take this and rewrite it down here. I can break that up, right, as x1 times the column vector a11, a21 through am1. plus x2 times this is how we first rewrote a system of equations as a linear combination of vectors. A12, A22 through AM2 plus dot 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 plus xn times A1n, A2n dot 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 through AMN. But this is really just C1, C2 through Cn. So in fact, AX by definition, we can think of it as, if A is written this way, we can think of it as x1 times C1 plus x2 times C2 plus through xn times Cn. So we can also think of it as just like a weighted combination of the columns. Maybe that's actually a better thing to write up here. Weighted combination. Sorry, let me try to write that as something better. Weighted combination of the columns of A. Call it that. And so they're equivalent things. It's just that there's two different ways to think about matrix times vector. I would say when I compute them myself, I tend to think of it this way as doing the dot product. But conceptually, there will be really good reasons to think about it this way. All right, and I'll stop there.